So we are again continuing our discussion on generating continuous random variables, and this time we're going to pay attention to something called the ratio of uniforms method. This is probably going to be the last really major algorithm we learn about in the continuous random variables case. Now, ratio of uniforms is a fairly powerful method in the sense that when it works, it can work really well. But there are often situations it's not very practical or useful. But again, when it works, it can work really well. Okay, so let's dive right into it. Okay, the main ratio of uniforms method is dependent very critically on a theorem, and we're actually going to go through the details of the theorem and the proof as well, because it really gives us some insight into what's actually going on. Okay, so here is the theorem. Again, remember, our goal is to sample from a continuous a distribution, a continuous random variable, and get realizations for continuous random variables. Now, our fundamental underlying theorem is the following: that let f, small f, be some target density implying that we want to sample from it, and let it have a distribution function, capital F. Okay. Now we define the following set. It's quite arbitrary, but we define the set C such that it is the set of all tuples u and v, okay, all tuples u and v, such that u is bounded between 0 and bounded above by square root of f of v by u, where this f is the same f, is the same f as this. Okay, so it's the same target density. And this weird looking C, set C, is going to be our sort of critical object that we're going to be looking at. Now, if set C is a bounded set, okay, only if it's a bounded set, then the following result says that let U and V, capital U and capital V, be a combination of random variables that are uniformly distributed over this set C. Then V by U is distributed according to F. Alright. This is the theorem. Again, so we have a target density and the target distribution, and the target density then is used to define a set C, where C is this tuple U and V, such that the U parameter, the first parameter of this set, the first element of this tuple, is bounded below by 0 and bounded above by square root F.V, U. And we want to look at all such possible tuples u and v and create a set C from it. If that set C is a bounded set implying that on the u and v plane, it looks, let's say, something like this. It's bounded, right? So it cannot look something like this where it's not bounded. Okay. If it is a bounded set, then you consider the uniform distribution over the bounded set. Okay, so the uniform distribution over the bounded set, just like we considered uniform distribution over a circle, right? Just like that, and then take any point that is uniformly distributed over this bounded set, and that point's v coordinate by u coordinate. So v by u, if we take a ratio of those two coordinates, then that will be distributed according to F. Okay. Now we will show that we are actually going to show this result, right? This is our goal. So we're going to prove this result. And the way to prove this result is actually again by a transformation method. What we'll do is we'll look at this object v by u, okay, and show that v by u is distributed as f via considering this mapping v by u from our current mapping of u comma v distributed over the set C. So this is what I mean. We'll show that the density of z equals v by u is f of z. Okay, and this f is the same as a target density. Now, in order to do this, first what is given to us in our theorem is u comma v is uniformly distributed over a set C. This is what is given to us. Okay. So that means what is the joint density of u comma v given that it's distributed over the set C? Well, the joint density is just going to be the support, which is the set C, divided by the area over the whole of the whole set. Because it's uniformly distributed, our mass or the density cannot be dependent on u or v because it's uniform. So that means the actual PDF of f of u comma v is the indicator that uv is in C, that's my support, and 1 divided by the volume of this set or the area of this set, which is the double integral over the set C of du dv. Okay. Now we have this joint PDF of u and v distributed uniformly. Now what I do is I look at the following transformation. So I do a bivariate transformation where I consider the transformation u comma v going to u comma z. So the second component is z, which is v by u, and then the first just remains u, right? That I don't want to change. Okay, because I'm not really interested in the first component. I just want the marginal distribution of z here. Okay. So then, according to this mapping, I am just setting u to be equal to u. So that part is simple. And I'm setting z to be equal to v by u, which means I get v to be equal to uz. Alright. Now, in order to find the final density of f of u comma z, u by u comma z, I need to know, so this I basically get f of u comma z of small uz is nothing but the Jacobian again times f of u comma v, right? U comma v. That's basically what my density will look like. Now it's fairly straightforward to show, and given that we've done a Jacobian calculation in the previous lecture, I will leave it up to you as homework. So this part is going to be homework, but it's fairly reasonable to show that the Jacobian for this transformation is nothing but u. So basically now this Jacobian becomes u, and then I get integral over the set C of du dv, right, of the indicator of 0 less than equal to u less than equal to square root of, now I can't put square root of v by u anymore because this is no longer a function of v. So I put square root of z because my transformation z is the transformation of v by. So this finally becomes my PDF of the transformation. Now I'm more or less set up. All I need to do now is find the marginal distribution of z. And if I can find the marginal distribution of z and show that the marginal distribution is nothing but the desired distribution f, then I'm done. Okay. So in order to find the marginal distribution of z, I want to integrate out u from this joint distribution. Okay. So to integrate out u, I get just marginal density f of z. F of z is integral of the joint density times du, integrating out u. Now I notice that this, even though this is just an integral, I'm writing this as integral of du dv, but this is just an integral, it's a constant. So I can pull that outside and I get this indicator means that u is only between this interval and it's 0 otherwise. So with 0 otherwise, then this integral simplifies to just 0 to square root f set du, right? Because everywhere else this indicator is 0, right? So all other parts of the integral go away, right? But now this is, I can integrate this, and when I integrate this part becomes u square by 2 from 0 to square root fz. Okay, and that gives me back fz by 2 divided by the integral. Okay, now up till here we are okay, hopefully. Now here's the issue. I get that the marginal density of Z, which I want to show is Fz, is not really Fz. The marginal density of of Z over here turns out to be our desired target density divided by this constant. I don't want that constant. I just want to show this is equal to this. Okay, but this is where we use the fact that both the marginal density of Z and F are densities. So if they are both densities and they have the same support, right, then they both integrate to 1. So if I integrate from minus infinity to infinity, then f of z is 1 because it has to be a density. Then the right hand side I have to integrate as well. But then this numerator is a complete density, so that integrates to 1. So I get this thing over here. Now what I will do is I will take this and this. Okay? Oops. I will take this and I will take this. And I will see that when I equate them, I get that the integral of the set C, as in the area of the set C, is half. That is really interesting because this set C depends on my density, but it depends on my density in such a way that the integral is actually turning out to be just half. Okay. Alright. And so this implies if the integral is just half, then I can see that this thing becomes 1, right? And I get f of z is equal to f sub zz. So I get that the marginal distribution of z is my desired target, marginal density of z is my desired target density, and thus that means that z is equal to v by u has the desired target distribution. Right. So this helps us prove the actual theorem. Now the question is, how do we actually use the theorem? So the way we'd like to use the theorem is, we'd like to, given a target density, we'd want to construct the set C, draw u and v uniformly from the set C, right? And then v by u follows f. This is what we'd like to do. Okay? We draw uniformly, and once I have a uniform draw over the set C, I take its second component divided by its first component, and that should be my desired draw according to this theorem. Well, the issue is this set C, what is its shape like? I don't know, right? The set C can look quite weird, right? So I can have the set C look something like this. I can have the set C look something like this. As long as it's bounded, that's all I care. Then the theorem will work. So what is the shape of C and how do I actually sample from this set C? Okay. So like I said, so C looks quite complicated. So how do we uniformly draw from C? Well, the good thing is that we need not actually know exactly what the shape of this set C will look like. All we need to really do is, just like the circle example, if I have a set C that looks something, let's say like this, okay, all I need to do is bound this set C inside some box. It doesn't even need to be the tightest box. I just need to bound this set C, enclose this set C within some box. Okay. So this is my box, right? And this is my set C. Now, if I have enclosed it within the box, then it's the similar way that we did for sampling from the circle. If I draw uniformly from within the box, okay, and exclude all the parts that are outside the box, oops, I guess that doesn't work. If I just exclude all the points that are outside the box and only choose the points that are inside the box, right, then that is going to be my desired distribution, right? So I just do accept, reject from inside the box. Okay. So that's our answer. How do we sample? We think back to the AR technique we used to draw uniformly from a circle. If C is bounded, if a C is a bounded set, then we can enclose it in a rectangle. So that's the beginning part. If it's not a bounded set, we can't enclose it in a rectangle, right? So once we enclose it in a rectangle, we can use accept reject. So now the question is, what is the rectangle? Well, recall that we have our x-axis is the u-axis and the other axis is the v-axis. Now u is bounded between 0 and square root f of v by u, right? V by u can take any value, so basically it's square root f of x, okay? And v I don't know, but I know this much, that u is always bounded below by 0, which means that 0 is probably a lower end for the box. And then I need to find the upper end of the box, okay? And so I need to find what this upper end will be and what these lower ends of the box will be. Then I can actually enclose my box, right? So I need to find A, which is this end, my B and C, which are these ends. Okay, so I need to find A such that U is between 0 and A, and I need to find B and C such that V is between B and C. Okay, so how can we do that? How can we do that? Fairly generally. Okay, so first I notice that square root f of x is the upper bound for u, sorry. Now, if the square root f of x itself has a supremum, so square root f of x itself is bounded, then that is my natural largest value this can take. So it's the largest value this can take for any given x, and the largest value that can take gives me the largest value u can take. So 0 is less than equal to u and is less than equal to square root of f of u, v by u, which is naturally less than equal to supremum of square root f of x, square root of f of x, which I denote as A. So A I get very easily, and given any target density, if I can find the supremum here, then that gives me A. Okay. Now I need to find B and C. Okay. But in order to find B and C, I note that inside the circle, for any point inside the circle, x has to be equal to v by u, right? A dot x I will map to v by u, right? This implies that if I bring this onto this side and this onto this side, that v by x is equal to u. Now v by x is equal to u, but u is upper bounded by square root f of x. Okay, so then I get v by x is upper bounded by square root f of x. I'm just moving things around here. Okay, now what I want to do is I want to take this x onto this side, but I can't do it very generally because this x can either be positive or it can be negative. Now if I take a negative value onto the other side of an inequality, I get the sign of the inequality changes. So I can't do it without thinking. So what happens is, what I will do is I will assess, okay, is my x positive? If x is greater than equal to 0, then I can take it on the other side without changing the sign. So v is less than equal to x f square root f of x. Now this is for all x, so I can upper bound by supremum x square root f of x, and that gives me c, right? So I get a natural upper bound on v. If x is negative, then v is actually greater than equal to x square root f of x, okay, which now I know is greater than equal to the infimum of all the negative values x can take of x square root f of x. Now because this is a lower bound, this is naturally going to be my b. So in this way I get my b's and my c's, right? So that gives me the form of what B and C will look like, and that can give me finally the actual box. Now notice that if either square root f of x or x squared f of x, right, if either of these are unbounded, then that means that either on the u-axis the box will keep on going, or on the v-axis the box will keep on going, right? There is no way to actually get an enclosing box. Right? It's either going to keep on going in one direction or keep on going in the north or south direction. And because of that, that will imply that C is not actually bounded. So if you can't actually get these to be finite or bounded, these turn out to be unbounded, then this will imply that C is unbounded and the method won't work. Okay. So now we found the rectangle. Rectangle is 0, A, B, C. And what we'll do is we'll propose from this rectangle and check if the proposed value is in the region C. If it is in the region C, then we will accept it. Otherwise, we'll say we don't like it and we'll not go with it, right? So the final algorithm looks something like this. We generate U, V, which is uniform from 0 to A cross uniform B to C. So this is from generating inside the rectangle. Okay. Now, if U is less than equal to square root F of V by U, this part, this part is asking the question, is the draw in C? If it is in C, then I want to set X to be equal to V by U. Okay, because it's in C, my accept reject part is done. Then I will get that I've gotten a representative draw from X if I take its second coordinate and divide by its first coordinate, right? And that's my return value. If it's not in the region C, then my accept reject algorithm has not worked, and I go back to step 1 and draw again from the rectangle, right? So this is actually an accept reject embedded within this, okay, within this ratio of uniforms. It's if we can actually draw uniformly from the set C in some direct way, then we will not need accept reject at all, right? So that's exactly what this is saying, that steps 1 and 2 in algorithm 1 are implementing an accept reject to sample uniformly from C. Now the question is, in accept reject algorithm, we know that we have an understanding of the efficiency of the algorithm via the constant on the upper bound constant C, that's a different C in accept reject, right? That is, it is the constant sup F by G, right? F of U, V by G, U, V, where this G over here is the proposal, right? Now this G is my actual rectangle in this case, or the uniform distribution over the rectangle in this case, and my target distribution is the uniform distribution over the set C. So that's this target here, and the proposal distribution is the rectangle uniform distribution over the rectangle. But the uniform distribution over the rectangle, G of U, V, is nothing but 1 over the area of the rectangle times indicator of the support, right? Indicator that U and V are inside the rectangle. But what is the area of the rectangle? The area of the rectangle is nothing but 1 over A times C minus B, right? Because that's the sides of the rectangle. And so when I solve this, I get that the constant is 2A C minus B, where over here I'm also using the fact that integral of C du dv was actually a half. This I proved, this I obtained in the proof of the theorem, right? The theorem. Okay. So this finally I get that this is the efficiency, which means according to the accept reject that the probability for acceptance of the AR accept reject algorithm inside the ratio of uniforms is 1 over 2A C minus B. So if the box is large, which means either A is large, or the U axis you have too much, or C minus B, the difference on the Y axis, the V axis is too large, then the probability is going to be small, and thus the algorithm will take a large number of loops to give one acceptance, right? And that makes sense. In the next video, we will do a few examples of the ratio of uniforms algorithm.